So here I have this problem I found that states, given a real number x, let floor of x denote the greatest integer less than or equal to x. So if you have 6.4, that turns into 6. If you have 5.6, turn into 5, etc. Right? Kind of just rounding down. For a certain integer k, there are exactly 70 positive integers n1, n2, up to n70, such that k is the floor of the cube root of n1, which is equal to the floor of the cube root of n2, and so on, until you get to the floor of the cube root of n70. And k divides n sub I for all I such that I is from 1 to 70. Okay. So if k divides n sub I, we could say that n sub I is equal to some k times some r sub I, right? And it says find the maximum value of n sub I over k for I between this interval. Okay. Now, when I was first looking at this, I had no clue where to start. But the trick is not to worry about the floor thing, because all the floor thing is saying is that the cube root of n sub I is between k inclusive and k plus 1 exclusive. Okay, so now since we have an inequality, we can cube both sides. So we have k plus 1 cubed and then k cubed, right? Now, the next thing we can do is we can expand this. We can expand this k plus 1 cubed. And that's a very simple expansion. I mean, if you don't know it, that's okay. It's just, you could expand it manually, or you could just remember the expansion, because it pops up a lot. It pops up a lot, so it would be best to memorize it. Okay. Well, okay, our n sub I is not any number, or any integer. It has to divide by k. So one thing we could do is we could do k cubed is less than or equal to k times r sub I, which is less than k cubed plus 3k squared plus 3k plus 1. Oh, wait, we're dealing with the integers, and we add 1, and that's strictly greater than n sub I. Then if we just get rid of that 1, that's going to include this number. And the motivation for why you might want to do that is because now you have a k here, a k here, and a k here. So we can divide out the k. So k squared is less than or equal to r sub I, which is less than or equal to k squared plus 3k plus 3. So we have our max for r sub I. Our max of r sub I is k squared plus 3k plus 3. Okay. But it says up here, there are exactly 70 positive integers that this holds. Okay? So the count of this set of integers should equal 70. So we have k squared plus 3k plus 3 minus k squared plus 1 is equal to 70. The k squareds cancel, and you simplify to get 3k plus 4 is equal to 70. And that's a bit of algebra. You get k is 22. Okay, so our k is 22. Now our maximum value of n sub I over k, here's our r sub I, which is n sub I over k. Oops, that looks like a factorial. Oh well. That's a letter I. Let me redo that. Okay. So we have this. So and we have our k is 22. Well, what we can do is we can get our max r sub I, because now we know what k is, what k has to be, and our max r sub I is k squared plus 3k plus 3. Okay, well our k is 22, so this is just going to be 22 squared plus 3 times 22 plus 3. 22 squared is 484. Kind of looks like a 9. Let me redo that. 484 plus 66 plus 3. All right. And so how I did 22 squared, by the way, is if you do the expansion in terms of 20 plus 2 squared, you could also just use your standard multiplication, but this is a nice trick. You know, a squared plus 2ab plus b squared, so you have 20 squared plus 2 times 2 times 20 plus 2 squared. You get 400 plus 80 plus 4, and that'll of course be 484. Okay, so let's add it all up. 484 plus 69, that's a 3, that's a 1, that's a 5, carry the 1, 553. And 553 is your answer for this problem.